Hi everyone, today I'll talk about efficient detection of long consistent cycles and its application to distributed synchronization. Our work aims to improve camera orientation estimation in structure from motion. Here we demonstrate images of the Eiffel Tower from different perspectives that are used in structure from motion to reconstruct the 3D structure. The camera orientation estimation problem in this context asks to estimate the ground truth camera orientations of multiple cameras given their corrupted relative orientations. We encode the relative orientation between two images by rotation matrices and refer to them as relative rotations. We also encode the ground truth orientation of each image by rotation matrices and refer to them as absolute. Next, we formulate the rotation synchronization problem. First, it assumes a viewing graph with nodes from 1 to n, the label of images. As we see in the picture, in the viewing graph there are 5 image nodes and 5 edges. For each image pair with an edge, we observe their relative rotations, which are represented as rotation matrices. Some edges have corrupted rotation matrices, which are called bad edges. Other edges are called good edges. Rotation synchronization solves the absolute rotations for each image given the relative rotations. In the picture, we want to recover the absolute rotations from R1 to R5. The absolute rotations are often solved by weighted least squares, so the edge weights are critical to the performance. In this work, we focus on estimating a reliable set of edge weights by exploiting cycle consistency. Our proposed method is called long sync. C-cycle consistency is defined as follows. We denote the cycle from ik1, k1, k2, up to kc-2j, and finally ji as L. Note that L contains C edges, therefore we call L as a C cycle. We say L is consistent if RL, the cumulative rotation along cycle L, is equal to Rij. Below we see an example of cycle consistent images 1, 2, 3, 4, and 5. Their relative rotations satisfy the cycle consistency constraint above. It holds true that if edges of the cycle L are good, then the cycle L is consistent. We have the natural cycle inconsistency measure dL defined as the distance between RL and Rij, and we want to infer the edge corruption levels, the distance between Rij and its ground truth, from the cycle inconsistency measure dLs. Previous algorithms are only scalable for c equal to 3. Our long sync algorithms, however, modifies a previous algorithm named CAMP by utilizing matrix operations for better scalability when using longer cycle information. We can guarantee that, under reasonable assumptions, one can exactly recover the corruption levels by long sync. Our method enjoys a number of advantages. It utilizes longer cycle consistency, which is useful for scenarios where 3 cycles are not available, such as bipartite graphs. Also, it enjoys better scalability, and it is the first practical algorithm that infers edge corruption levels from longer cycle inconsistency information. We test long sync on phototourism data. We refine the distributed synchronization pipeline by incorporating long sync weights. Here's an illustration of how 4-cycle long sync is used to estimate an intercluster rotation between cluster K and cluster L. Note that the relative rotations between clusters form a bipartite graph. To synchronize these rotations, we first perform long sync with 4 cycles to estimate the weights of these intercluster edges, since there are no 3 cycles for a bipartite graph. Then, we take the weighted average of relative rotation estimates from each edge as the initialization of the L1 rotation averaging. We summarize the results on phototourism here. As we can see on the comparison plot, our method achieves a much lower mean and median error than iterative weighted least squares without significantly increasing runtime. We summarize the conclusion in the last slide. Thank you for listening.